So continuing on with section 7.12, it says here that alcohols can also be used in substitution and elimination reactions and used as starting materials to make alkyl halides and alkenes. So if I take a primary alcohol and I treat it with hydrogen bromide, I can go from the primary alcohol to the primary alkyl bromide in this case, and I also lose water. So what's going on here? It says we need strongly acidic conditions to do these reactions because hydroxide, I should put this hydroxide, is a bad leaving group. But H2O is a good leaving group. So what happens in the first step is that you get a proton transfer where the hydrogen bromide, which is acidic, protonates the alcohol to form the oxonium. And now in my loss of leaving group in this step, okay, I'm losing water. So this is water coming off of the molecule, which is shown over here in the end. So water is a good leaving group because it's the conjugate base of hydronium, which is a strong acid. But what's happening here is now that you've converted the primary alcohol into a good leaving group is that the mechanism proceeds in an SN2 fashion. So I get a nucleophilic attack by the bromide, and I get the loss of the leaving group simultaneously. So this is kind of interesting because we're converting an alcohol directly to an alkyl halide. So again, we're converting something that is a poor leaving group, right? An alcohol or a hydroxide, into something that's a good leaving group, a bromide. Furthermore, if we take a tertiary alcohol, so this slide deals with a tertiary alcohol. So it says here the mechanism will either be SN1 or SN2 depending on the substrate. So primary alcohols react via SN2 like we saw in the previous slide, but a secondary or tertiary alcohol will react via an SN1 type mechanism. So again, the same rationale applies in the first step, that hydroxide is a poor leaving group, so I do the proton transfer from my acid, HBr, and I convert the alcohol into a good, so now I have a good leaving group. So I lose water, and water is the conjugate base of a strong acid. I know I'm repeating myself, but it bears repetition. In the next step, after I form the carbocation, then bromide can come in as a nucleophile, and it attacks the carbocation and produces the tertiary bromide. So this is a little bit different mechanism in that in the first case, it was an SN2 reaction, the primary alcohol with HBr, but with this tertiary alcohol, it's an SN1 mechanism, SN1 at a time. First I get the proton transfer, then I get the loss of leaving group, then I get the nucleophilic attack. So strongly acidic conditions, we call these protic conditions, which would favor SN1, but since primary carbocations are too unstable to form, primary alcohols react via an SN2. So to recap, what I'm trying to say here is that a tertiary alcohol will react via an SN1 mechanism, but like I said on the previous slide, a primary alcohol will react via an SN2 mechanism. And you should know this. You should know both of these reactions. So a little bit about the elimination of an alcohol. So it says here, alcohols will undergo E1 elimination when they are reacted with sulfuric acid, so H2SO4, sulfuric acid. So in this example, it shows a tertiary alcohol, and it says you're treating this with concentrated sulfuric acid, and you're applying heat. And when I think of heat, I think of, removing water via evaporation. So what's happening here is that you're converting the hydroxide or the hydroxyl into a good leaving group, and then once that leaves, water can come in and behave as a base and abstract a proton. So again, the strongly acidic conditions are called protic conditions, which favors E1 for secondary and tertiary substrates. So this shows us the entire mechanism. So in the first step, we get our proton transfer to convert our hydroxyl into a good leaving group. We lose our leaving group here. Our leaving group is water. Water is the conjugate base of a strong acid. And then finally, in the last step, the the water ends up removing the proton to reform the hydronium. So let's take a look here. So in question 7.42, it says predict the major product for each of the following reactions. So in the first case, I have a tertiary alcohol and I have HBr. So as we just discussed, this is going to proceed via an SN1 mechanism. Now it doesn't ask us to draw the mechanism out here, but I'm going to do it just for fun. So if we draw the Lewis structure of HBr, we can draw the curved arrows for the proton transfer that convert that hydroxyl into a good leaving group. So I can draw the good leaving group. You can draw it like this, or you can draw it as OH2 with a positive charge. Either way is fine. But now I'm going to lose, oops, fix that, there we go. I'm going to lose that leaving group like this. So I'm going to lose my leaving group, and I end up with a tertiary carbocation like this. So there's my tertiary carbocation. And in the last step, my bromide that I formed over here in the first step, when I broke the bond between the hydrogen and the bromine, my bromine is going to come in as a nucleophile, and it's going to attack that carbocation to give me the tertiary alkyl bromide. So this is my product. So let me switch my pen here, and let's take a look at the last one. So it says, predict the major product of this reaction. So it says here I'm taking a tertiary alcohol, so again the same tertiary alcohol, and now I'm treating it with concentrated sulfuric acid and heat. And as I mentioned previously, in this case, the elimination mechanism is going to predominate. So there's two possible elimination products, and I'm going to go over this one a little bit quicker. So you would probably notice that there's these beta protons here, we'll call those H1, and then there's the methylene beta protons as well. So if I were to pull over, or excuse me, abstract the proton, the H1 proton, I would end up with this alkene. Okay, I'd end up with this alkene, and then if I abstracted the H2 proton, I would end up with this compound, so 1-methylcyclohexene. So there we go. And in this case, the more substituted alkene is going to be the major product. So this would be our major product. And of course, if you want to write that that's the Zaitsev product, that's no problem. All right, I hope you find the second section of section 7.12 about alcohols. I hope you find this video helpful as you continue on in your organic chemistry journey.